still have two exercises, this and another one. In this exercise, we ask you to design a PID controller, and the last exercise, exercise 8, we ask you to design lead-lag compensator. So we combine the lead and lag together. Here is PID controller. So given the system of the following figure, design a PID controller so that the system can operate with a peak time that is 2/3 that of the uncompensated system. So the system should operate at a peak time 2/3 the uncompensated system. So you need to add here PID controller KPKIKD, in which the peak time will be 2/3 the peak time of the uncompensated system. Okay, and at a 20% overshoot with 0 steady state error for a step input. Basically that's it. So let's go for quickly. So now my closed loop system S+8, let's check. S+8 0, S+3 6 and 10. So S+8, S+3 6 and 10. This is open loop transfer function 4 for me. So alright, open loop transfer function. I close this one. Open loop transfer function 4. Okay, so again, I don't need this for in this chapter for the diagram. Also, it's a good way to design a controller. We'll learn in the next chapter. So an overshoot of or an overshoot of 20%. So this is obtained. Of course, you go over and we keep increasing and up to the 20%. Less, even less. 28, 17, 21. So this is the one I obtained previously. It is 19.9, so 116. And at a peak time equal to 0.306. Alright, so the new peak time will be 0.306 over 3. So this overshoot I obtained at k equal 116 using the CISO tool, and that's my peak time. Of course, I can find omega d in case needed, and in case I want the settling time, I can also look at 0.713. Alright, let me check. Settling time 0.713. So here it looks like I'm having it 0.8338, and they are the same. Maybe the minor difference due to the fact that maybe I'm at 20 overshoot, 21, so on. So it's in this range. So up to now, what's the question? The question is design a PID controller to get a peak time 2/3 that with this overshoot and with a steady state error of 0 for a step input. What's the steady state error now? So see now 1 minus 0.8, so like around 0.2 steady state error. So we need to design a PID controller. What's the strategy? How to go with? So now we will learn how to go with. We will actually design first a PD controller, then later we design a PI controller. Design a PD controller first to satisfy the transient requirement of the system, and this is very important. We design the PD controller to satisfy the transient requirement of the system, mainly the overshoot and peak time. Those are the transient requirements. If you wish, overshoot and peak time. Then later we design a PI controller to satisfy all the requirements as overall. Okay. And this is a strategy that you need to use when to design PID controller. Design PD, then we add PI. And at the end, so your total controller will be, if you wish, will be S plus ZZ over, okay, ZC1, if you wish, S plus ZC2 over S, and this will be your PID. Alright, even so, we know it's not recommended to use pure integrator, pure derivative. This is pure derivative, like you have, but this is why it's PD, because it's equivalent to, PD is KP plus KDS. And this is equivalent to taking, if you wish, in here taking like KD equal 1, and this is KP. Simply as that. Taking KD equal 1, and here is the KP value. So it's PD pure derivative, and this is not recommended. Pure integral, and this is not recommended. And this is also equivalent to, this is PI actually, not equivalent to PI. This is PI. Because PI is KP plus KI over S, then S common, KP S plus KI, and you can see S plus ZC, so it is a PI controller. So you need to design PD controller to satisfy the transient requirement of the system, overshoot and peak time. Basically, what you need to do, you need to add a real zero, S plus ZC, so a real zero, and adjust it and the gain to satisfy the requirement, the overshoot and peak time. They are now overshoot is 20% and peak time is 0.2, because 2 over 3 this one 0.2. So let's go over it. Now I will add 0 with locus, adding 0 to satisfy the. So now the question is where to add the 0. So where you want to add the 0? Do I add it here, there? Well, at the end you need to satisfy your requirements. So as a point to help you is, I suggest to first draw the design requirement on your schematic. So settling time, peak time, and damping ratio. So damping ratio of 20. We're not taking them, let's take it as overshoot, less than 20. Am I right? So less than 20%. Alright. And peak time less than 0.2. Yes, peak time less than 0.2. Well, we never did a design requirement for peak time. Peak time is pi over omega d. So therefore, if that's my peak time, so then this is equal to pi over omega d, and therefore my omega d equal to pi over tp nu. So my omega d nu, if you wish. So it is pi over 0.204. Pi over 0.204, which is 15.4. Alright, so this is 15.4, and this is your omega d. So radian per second. And if you know omega d, so basically, if you say, usually we say the settling time is the peak time, as a condition is we favor to be less than or equal to 0.204, then pi over omega d is less than 0.204, then omega d is more than pi over 0.204, which is 15.4. So omega d is more than this value. You could draw it, but here is a tricky way to draw it, like, because if you go to the design requirement, there is nothing said as omega d. You have natural frequency if you wish, so omega n, you can draw a circle, but you have percent overshoot damping ratio settling time, but you don't have omega d. Well, one tricky way to go is to go region constraint, and in here we know your omega d should be 15.4, so like somehow here, and then your design requirement becomes only this place. Okay, so this is omega d and symmetric in here. So then we add this line. This line, it has 0 0, it has 0 omega d. So that's the point here, if you wish. It has 0 omega d, and omega d equal to 15/4. So at the real axis it has 0, and the imaginary axis you have 15/4. Alright, and another point, maybe I take this point here, I take this point here, and this point has -10 and 15.4. Alright, so in the real axis you have -10, and here you have 15.4, and then you draw the curves that you wish. Okay, and this is your allowed region, of course. Symmetrically you can do it in this way. So now this is your allowed region. This helps you a little bit in finding the zero, where you want to put the zero to satisfy your requirement, overshoot and peak time. We said we want to design a PD controller to satisfy the transient requirement, which is the peak. So the transient requirement are the peak time 0.3 over times 2 over 3, so which is 0.2, which is reflected by omega d, and overshoot, which is reflected by this line. So adding 0, of course, is good because it will pull the root locus, or reshape the root locus to the left. Okay, so let me add 0 then. So then, clicking on it, I find it and add 0. Where to put your 0 to be in this region? Well, it's easy to guess, so maybe I put it here. I know it's not gonna work, but I'm just showing you how things will move. So then, you see, now I'll never be in this region, how easy things will move. Okay, so then keep moving my z, keep moving my 0. It seems like this 0 is alright. If you wish, let me go back like this. and try to edit the constraint here. Don't go up to -10, maybe go to -40. Okay, so -40. Okay. Still not satisfied. There is no root locus, doesn't. And keep in mind, this is a first order approximation because it's not a canonical system. Your system is not canonical system. The system by itself, I believe it's not canonical. It's higher order system with 0, and now you're adding a 0 on it. So it is first, keep in mind that it is a first order approximation. All right. So then here, okay, I'm fine with. Let's try to change the gain to be in this region. Okay. So I'm in this region. Well, with an overshoot of 11 and with an overshoot of 11 and peak time of 0.1. The requirement is peak time less than 0.2 and overshoot. Now, if the question clearly saying peak time equal to that and overshoot of 20 means you need to be at the intersection. You need to design your controller to be at the intersection to satisfy both. And keeping in mind this is the first order approximation. So can I do it in a way to intersect it somewhere here? Yes, sounds like this is fine. I'm intersecting it here somehow. So now if I 20, I go to 20. Of course, keep in mind it should not be the intersection exactly because it is not a canonical system. So here 21 overshoot 20.8 something. Okay, 20.1. So then and a peak time of 0.18, which is 0.18. So now, which is good. Well, here I over-designed the peak time to compensate the decrease in speed when steady state error is added. Basically, what he's saying here is like when you later on add the PI controller, this will slow down the system. So you'll have decrease in speed, right? So you slow down the system when you're adding the PI controller to compensate for the steady state error. You will slow down the system. So it's slow down. So then when it's slow down, make sure will be still satisfying the requirement, which is less than 0.2. So then, okay, let's keep it 0.18. So over design a little bit in the sense when you're adding the PI, you will be compensated for. So that's what we call over design. Well, you compensate for the addition of the PI because PI will slow the system down. So more likely the peak time which is here, more likely it will shift to here. But it will shift in the sense still less than 0.2 because 0.18. Maybe I can over design more, but let's keep it this way. And this is the PD controller. I store it. I can name it PD if you wish. Okay. It looks like I cannot name, so we know this is a PD controller. Restore view. That's how it looks like. So next step, we add a PI controller. Basically what I will do, I will add pure integrator at the origin, and I will look for a 0 in a way to satisfy the overall requirement. Okay, I'll add a integrator, and I will add a 0 in order to satisfy the overall requirement. But what are these overall requirements? So I need to add 0 now. But what are the overall requirements? Basically, I want to add, this is a PID controller. PD controller was satisfying my requirement, my transient response requirement. Do I have any requirement on overall requirement? Basically, the remaining requirement is the 0 steady state error, which was not satisfied. So now by adding pure integrator, we are sure we are satisfied it. Then we add a 0 to bring the system to a stable, because the integrator is more likely to make the system unstable or decrease the stability of it. So now we need to add a 0. And where to put the 0 is really not necessary to think a lot about, because this is a 0. You can take it, put it anywhere, starting from any place to any place, and then look to the overall design requirement. Okay, 20 with 0.2. So I can consider this 0, that I pick it arbitrary here, and check if I change my gain, I can reach my requirement. 20, 0.17. It seems the one I pick is alright. So look at it. So now this is the PID control. The one I pick is here at 1.7 somehow. So this is 0 I pick. 0 previously found was I put it here. So this 0 I put it at 1.74, and it looks like it satisfied somehow my requirement. Okay. Which is 20% overshoot. Overshoot with a peak time of 0.194. Alright, 0.194. So you see 0.194 less than 0.2. So I compensate, but you see it is slower, a little bit slower. Let's compare it with the old design I saved here. So in compare design, I compare this design with the design one, and we see how the system becomes slower, but I still having same overshoot, and with the difference of that, like I have 0 steady state error with this design. And that's the exercise is about.